All right, we've processed the IDF vector. It's stored in the database as up arrow IDF. We've gone through the database and removed those instances of words whose IDF value or whose IDF weight was below a certain threshold. And now we can proceed to do some things in parallel. Up to this point, we had to do things consecutively because they depended on, each step depended on the previous step. Now we can do a number of things in parallel. These are the term-term correlation matrix. The basic term-term correlation matrix calculates the number of times terms co-occur with one another in a document. So if term A and term B co-occur in 5 documents, the value in the square matrix, the term-term matrix, will be 5. We'll play some games with that later on and mitigate it, get some more refined measures of similarity than just raw counts. But we start off there. We can also do the proximity matrix. That's the same, very similar to the term-term matrix, but it also adds in the proximity of the words in the original documents. So if term A and term B co-occur in 5 documents, but they co-occur very close to one another, that's considered more important than them simply co-occurring but at a great distance from one another. If you remember back when we created the document term matrix, we put at a 3rd level in the matrix the location in the document where the term occurred relative to the start of the document. So, and we'll use that information to come up with a different form of the term-term matrix, one that takes proximity into account. This can be done in parallel with the regular term-term matrix. Also, there's the document-document matrix. In the document-document matrix, we're trying to find those documents that are similar to one another. And the first level of similarity is how many terms do they share in common. So we can calculate that at this point because we've got all the terms. So we can calculate a document-document matrix, and we can find out if for document A and document B, how many terms they have in common. That's a base level indicator of similarity. There are others we'll get to. Also, the discrimination coefficients. That's an alternative weighting scheme. Some say it's better than IDF. It doesn't really seem to be, but it is an alternative system. We'll look at it in a little bit, but it takes a lot longer to calculate. IDF is extremely fast, and it's quite good, but the discrimination coefficients can be calculated in parallel at this point in time as well. So we got proximity, document-document, term-term, and discrimination coefficients we want to process in parallel. How do we do that? Well, in my version of MUMPS, there's several different database backends. The slowest would be using the MySQL or PostgreSQL as the database backend. They're fine systems, they're ACID compliant, and so forth and so on, but they're not real fast for a lot of high-speed transactions. So that would be the slowest. The next fastest would be the client-server version. In the client-server version, you have multiple instances of MUMPS clients and a background daemon or server that processes database requests. In this system, it uses my own native B-tree database system. It's faster than our relational database backends, but it's still not the fastest. The fastest would be the standalone version of MUMPS. In the standalone version of MUMPS, read-write can only one instance of the read-write version can run at a time on a database. So if I have a set of key.dat and data.dat, those are the 2 database files in my system, only one instance of MUMPS in read-write mode can be operating on that. However, there's also a read-only version of MUMPS. When it creates the system, you'll notice there's not only an executable called MUMPS, there's also an executable called MUMPS cap-R cap-O. That's the read-only version. Now, the read-only version, you can have any number of instances running simultaneously on the same database. There can be no read-write version on that database, but you can have as many read-only versions as you want, and we will use that. Now, when we start running these programs, 2 of them are going to be running on read-only mode, doc.1.mumps and tt1.mumps. They'll be working on the same database, and they'll be in read-only mode. Proximity.mumps will be running on its own copy, and it will be in read-write mode. Likewise, discrim.mumps will be running on its own database, and it will be in read-write mode. Proximity.mumps and discrim.mumps both alter their particular databases, but the alterations in the end are not kept. When we're finished calculating the proximities and the discrimination coefficients, we will write them out to a file, and we will then discard the database in which the calculations took place. We don't need them any longer. We make no changes, of course, in the database for doc.1 and tt1, although we do write out data, and that data will be used at a later date. So essentially, we're going to have three databases created, three copies. And this is where the copies are created here. This copy 0, copy 1, and copy 2. When we come down to the first of them down here, we come down to tt1.mumps, and it operates on copy 1 of the database. The output of tt1.mumps goes to sort, it goes to unique, and then it gets written to a temporary file that will be used later on. Notice the ampersand, that means it's running in the background. As soon as we kick it off, we capture its process ID. $! Exclamation point and bash is the process ID of the most recently initiated process, and we store it in TT. Why do we do this? Because later on we're going to need to know whether or not tt1.mumps has finished. If it hasn't finished, we're going to have to wait, and in order to wait, we need to know the process ID. Likewise, down here, proximity.mumps kicks off. It's got a parameter, which is a minimum value, and then it's got copy 0, and that's the database it's going to operate on. It also pipes its output to sort and writes it out to a file, and there's an ampersand there, which also tells us that we're running in the background. Likewise, we copy its process ID, again, for later usage. And then we see doc.1.mumps. It operates on the same copy 1 as tt1.mumps did up here. So they're both operating in read-only mode, obviously. And the output is written to a temp file, and we will use that temp file later on. There's also a parameter there, which is based on the minimum weighting that we will use. We also capture its process ID, and we're off to the races. Then finally down here, discrimination coefficient is calculated in discrim.mumps, which, there it is here, which gets copy 2. Its output goes to sort and finally gets written out to a text file. It runs in the background. And we capture its process ID likewise. So at this point in time, we've got tt1.mumps is running up here, and it's assorted sort, unique, and whatnot. We've got proximity.mumps running, and it's sort running as well. We've got doc1.mumps, doesn't have any sort or anything after it, but we've got it running, and we've got discrim.mumps running, and its associated sort. So we've got a lot of tasks running. And if you get a multi-core machine, this will really run quite fast. The extra database overhead by having more copies of the files are not terribly big at this point. You make it more than make it back by the amount of speed increase you get here. So let's look at one or two of these. Let's look at tt1.mumps to see here. tt1.mumps, there it is. You see the RO. What does it do? Well, there's a database command that tells it not to use key.dat and data.dat, but use the use such and such .key and such .dat, and that's how it knows which database to use. The term matrix calculation starts off for each document, for each word 1 in a document, for each word 2, although I named it W1, for each other word on the same vector. We if they're the same word, we don't write it out if they're equal. That would actually be the count of the number of documents the term occurs in. We write out word, and we write out word with a blank in between. So we'll have these tuples. So if word 1 and word 2 occur, say, 3 times in a document, there'll be 3 instances there. If they occur together, say 100 times in the entire collection, there'll be 100 tuples there. When we go through the sort, all those tuples will be together. When we go through unique, we'll get a count of the number of each individual unique tuple set will get a count. And what is that count? It's the number of times those terms co-occurred with one another. Now, why do I do this funny thing here? Instead of starting at the beginning of the vector, I start at W, start at the word itself. I don't start at the beginning, and I go out through the end of the of the vector when I get back empty string. It means there's no more words. You don't need to recalculate starting at the beginning because you'll be doing duplicates. The term-term matrix, the upper diagonal matrix is equal to the lower diagonal. So you only want to calculate one diagonal. Unfortunately, you also, the first time through, the word you get back from order here is the word that you started with, because that is the initial word we do here. So W1 will equal W at least once. We can look at this with a, let's see, there's a program here. There's a minimal document term matrix. And you can see the situation. These are document numbers. These are the words going across. Obviously, your actual number of words would be very much larger, and your actual number of documents would be much larger. But we can see in this matrix, every time I run it, it's generated randomly. So let's see if we get one that's nice. All right, here, word 1 and word 3 co-occur. So there'll be a tuple out in the database with W1 space W2. They do co-occur again in document 6. So there'll be another tuple out there in the database, and that's the only. Well, they co-occur in document 2, in document 3, word 1 and word 3, in document 6. So actually, we'll have 3 out in the database. But when I do this calculation, let's just pick document 2 here. So I start off with word 1, excuse me, which occurs twice in this document. I then go. I say, I go across the row and I look for words that exist. The 0 means they don't exist in this document. So I will get word 1 and word 3 tuple. I'll get word 1 and word 4 as a tuple, word 1 and word 6 and word 7 and so forth. Then I'm going to start for word 2. What does it co-occur with? Well, I don't go back and calculate it versus word 1 because that's already been done. I've already done word 1 versus word 2. So I don't need to do it again. So I go forward from here and I say, well, I'm actually not going to do word 2 because it doesn't exist. Let's go to word 3. Word 3 is not recalculated with word 1. I go forward. I will calculate that indeed word 3 co-occurs with word 4, with word 6, with word 7, and these will be tuples that will be written out. And then I'll go to word 4, and I'll find out it's associated with word 6, word 7, and so forth. I don't go back to the beginning, because you'd be recalculating something you've already done. You'd be calculating the other diagonal, and we don't need it. All right, so that's what TT1 looks like. The others would be similar. The next one after that's proximity. Let me look at that. Proximity.mumps, and proximity.mumps, we are using the read-write version. It's got its own private copy of the database, and it runs the database command as before. It's more complicated. We'll go over the proximity code later on, but you can see it's much longer, and it actually does modify the database. These modifications are not important. We will discard them. The only thing we want to know is the result. We want to know how many times the words co-occurred, and we want to mitigate that or modify that based on how closely they co-occurred. That's the only information we want. Modifications to the database, when we're done, are irrelevant because we're going to write everything out. Here's where it all gets written out down the bottom here. It gets written out to a file. Okay, similarly, what was the next one? The next one down here would be doc1. It's going to be running in parallel. And there, you see there's the read-only version of it. There's the database command, and it's going to do something similar to TT1. We'll get into what it's exactly doing in another video, but it's running in parallel. And finally, the last one down there is Discrim. Discrim's running in its own database, read-write version. And you see there is just plain old mumps, the read-write version. There's the database command. And again, it's a fairly long program. We'll get into its details. There'll be a whole video on it. And it does modify the database. It does store things in the database. But in the end, we write everything out. And when we write things out, we're actually going to write out the discrimination coefficient, and we're going to write out the IDF value for the same word so we can compare them and see how they relate what the weights are for each word. There'll be different weights, of course, but relatively speaking, how are they weighting the same word? There are slight differences. Sometimes there's considerable difference. Anyway, we'll get to that later. Let me get out of here. So at that point, when we come after we've kicked all these people off. Well, I'm running. I mean, they're still on the bus. We've got TT1 sort and unique running. We've got proximity running. We've got who am I missing down here? We've got doc1.mumps running. We've got discrim, and it's got sort, and it's got stuff running. So everybody's running. We've captured in each case the process IDs, and then we come down here and we run wait.mumps. Wait.mumps is read-write. Notice there's no parameter for the database, so it's working on the main database, the actual one we carry forward, the one that's got all the important stuff in it. And it doesn't have an ampersand, so we will wait until wait.mumps finishes. These other guys are still running in the background as wait.mumps operates, but it's operating on its own, the standard database, key.dat, data.dat. So it chugs along, calculated. It's actually applying the weights, the IDF weights, to the document term matrix and the index matrix. Once wait.mumps finishes, we come down here and we wait for the term matrix calculation, tt1.mumps, to finish. That's where we use the process ID. We have to put a $ in front of it here. It's bash script. So it'll actually insert the value here, and we're going to wait for that process ID to finish if it's not already done. If it's already done, we just go right through here. If it's not done, we sit here and wait for it to finish. All the other things in the background still keep running, but we're not going to move forward until this one is finished. All right, when that does finish, we drop down and we will run tt2.mumps. tt2.mumps takes in that temporary file that we wrote out above. It writes out a file which is sorted, and then ultimately writes the term matrix.sorted.txt file. That is the final result of the term correlation. Notice this has no ampersand, so we're going to wait until this is finished. Anything else in the background that's running keeps running, but we don't move forward until this is done. We do some other things, and then you'll see that this sort of thing happens several times. Here's a Jacquard calculation that we're going to be doing, and it runs in the background. So we try to kick things off in the background as soon as we can, let them run. And there's only some things at this point which we have to do in sequence. Again, you can see a lot of them down here. We've got ampersands and so forth waiting for various things. And then finally down here, there'll be a master wait, which is way down the bottom here. The final wait down here, there will be one. I don't see it right now. It's which waits for everything to finish, and you'll see that when you run, waiting for all processes to finish. And once that's done, we then actually test the database. There's actually some testing done here. We actually try to do a retrieval, but we have to wait until everything's done at that point. All right, so that explains, I hope, the parallel nature of things. Now, we could do everything sequentially. I could do everything with the client-server version, but it takes longer. So I'm using it this way. What we're doing is still the same, but it tries to speed it up a bit. And we can actually, apparently I didn't type that exactly right. All right, so we actually look at it running. Let's try running it and see what it looks like on the system. See how much utilization we get. So say index.script. And let's give it 2,000 documents because that'll take a little while. And at the same time, I'm going to start up a process monitoring here. All right, so it's off and running, and we'll see the utilization. The utilization's up at the top here at the system monitor. You can see it's starting to rise. But at the moment, yeah, there's one of the tasks that's gone quite up to the top. Well, it went all the way through. Apparently everything worked, and we went all the way through. It just wasn't enough data to actually show up on the show the parallelism, unfortunately. But there is actually a full run, and we come down, we ask a question that had Staphylococcus aureus and antibiotics in it, and there are the actual answers. Well, we'll see it running. When you're doing a large database, all of your cores will be maxed out. Well, not all of them. I think at the maximum point there's only about 5 or 6 processes that get running. But it will make utilization of all those extra cores that you may or may not have. If you don't have them, it'll just run a bit slower. It'll still try to utilize everything. So we'll pause it here.